Okay, start stream. Next one, we need link to this stream, aren't we? Share. We click share button. Okie dokie. Next we put it in another window. Switch account. Here we are. Let's wait until window updated. And then paste link. Address is invalid. Okie dokie. Share. One more time. Create highlight video. Upcoming. Leave. Video link. Okie dokie. Screenshot preview. No. Order transform. Fit to screen. Let me answer. Super. So we have set up different applications. Okie dokie. Camera. Browser. Yeah. Terminal. Yeah. We'll see. Okie dokie. Audio. Okay. Let's check if we'll see appear on the top. looks no. Why this transform fit to screen? No. That's okay. And then we can rescale it, for example, this way. And then we can hide it and switch to the browser. So this is main window browser. We start with this one. Also we need a terminal. Yes. Perfect. I didn't catch why this and black corners are blacked. Next one, we need camera, terminal, browser, and we'll see. Browser, we will show command how to connect robot. We'll see. Cool. Terminal. Awesome. Good. Turn on camera. Turn on robot. Switch off notifications. We go to focus. Turn on disturb. Open applications. Terminal. RPI SSH and SSH tunnel. Yeah. Good. It's done. Open applications. SSH tunnel. Let's this one. We need this one. This is a RPI SSH, and this, for example, Rose Bridge. First to launch. Yeah, terminal. Next one, we need Safari. Next one we need ultrasonic, obstacle avoidance, and motor driver code. Terminal. So in Safari we need this one, these, and ultrasonic, publisher, ultrasonic publisher. Yes. Next one, obstacle avoidance. Yes. And motor driver. Good. And terminal. Here we are. Good. Terminal, close left panel. Now this one we don't need. Oh, нам еще Chrome. We need Chrome application. Yes, we need Chrome application. Yeah. So we need to add macro screen capture, Fox glow, display application, Chrome. Fantastic. Transform, fit to screen, maybe transform, stretch to screen. Great. We'll see. We will see. And this seems camera, browser, terminal. We'll see. And Foxglow and Google Chrome, Foxglow and Safari browser. notebook. Good. Hide OBS, OBC we don't need. So we can start, aren't we? Yes, start recording. Okay, so today we are presenting you a workshop how to create your own real robot with algorithm that avoid an obstacle. In this workshop we will discuss next topics. First one, robot platform. Second one, robot operation system that operates robots. Next, Foxglove to visualize our results. Then we will discuss basic knowledge about robotics that called coordinate frame. Next we will discuss obstacle avoidance algorithm. Then we will show you how to set up environment to run your own robot. Next we will discuss how can we do it in simulator, and another approach, simple approach without any robot operation system means. And then we will wrap up our meeting, our discussion, our lecture, our workshop, and answer on your questions if they are. If they are good. Give me a second, let me check. This message. Welcome to live chat. Good. Okay, robot platform. There are a lot of different platforms for nowadays robots. One of the most famous is the NVIDIA. NVIDIA provides its own platform called Jetson, and robot simulator called Isaac, and robot operation system that calls Drivos. Next one, more cheaper platform is Raspberry Pi. Today this is a Raspberry Pi 4 or 5. We create our robot on the platform that consists from the control board. Control board is the Raspberry Pi 5. Next one is distance sensor. Let me fix it. Control board, Raspberry Pi 5. Distance sensor is called ultrasonic HCSR04, motor wheel and motor driver. Okay, our software is written on ROS. ROS is a robot operation system. It's a set of software libraries and tools for building robot applications. Next, we need a Foxglow. Foxglow helps robotics teams explore, collaborate on, and make sense on the robot's data. We will use our Foxglow, this one. Main feature of this visualizing tool is that it is cloud-based, so you can run this Foxglow via your browser. We connect to our robot operation system via either WebSocket or via ROS bridge. It could be done, for example, this one. So you can open connection, for example, Foxglow WebSocket or via ROS bridge. We will connect to our robot and robot operation system via ROS bridge. And it helps us to check what's going on different part of our robot, like sensors and topics and nodes. Before to start discuss obstacle avoidance algorithm, let's dive into the robotics base topic, base knowledge about coordinate frame. Each robot has its own coordinate frame and it has 3 axes. X-axis, red axis, is always points forward of your robot. Green Y-axis is point to left hand of your robot, and blue Z-axis is always up, points to up of your robot. It helps us to understand how to implement our obstacle avoidance algorithm. So this algorithm is pretty simple. Our task is to control movement of our robot for the next rules. If there are no obstacle, our robot should move forward with the maximal possible speed. Speed can be changed from 0 to 1. 0 is the lowest speed, 1 is the maximum speed. Actual speed depends on the motor itself and wheels. So when you set your speed equal to 1, your robot will be move with the maximal speed. Okay. What if the obstacle appears in the front of robot? So for example, if distance to the obstacle becomes less than 50 centimeters, we should stop robot and turn it right along the Z-axis. So we should set angular speed around the z-axis to 0.5. It's a medium speed of your robot. Let's recall, the 0 is the lowest speed, 1 is the maximum speed. So when there's no obstacle, then linear speed along axis x is equal to 1. It means maximum speed. This is the Python code that describes this algorithm. You see, it's pretty simple. Next, we need to set up our environment. First of all, we should create a working directory on our computer. Next one, we need to go to the source subdirectory. Next, we should clone our Git repository. And then we should go to the ROS2WES. Let's make it possible. Okay, cd our working directory, our home directory, check what's going on, then we create this directory, then we go here, then we clone this repository. Ta-da! It's cloned. Good. Then we should go to the upper directory and install dependencies for all your robot operation system. And after that, we should build our packages. Let's check first of all what packages we have. Oh, So we go back. Then we clone our repository. Yes, it's created. Let's check. We have obstacle avoidance, ultrasonic, motor drive. Then we go to ROS2WES. Go here. cd your home directory, cd, okie dokie, and calcon build all packages, and wait when it finished. Good. It's finished, it's built. Next we need to connect to Foxglove. First of all, we need to create launch. For this, we open our terminal, and in terminal we should run first one. We should go to robot, okay, and create ROS-bridge WebSocket. WebSocket created. Then we need to go and create SSH tunnel. For it, okay, tunnel is created. After that, we can go to our Foxglove and connect to localhost. Yeah, and we see that connection established. We receive timestamps. It means now Foxglove connected directly to our robot, and we can check what kind of topics on robot operation system now working. So we create panel, for example, topic graph. Let's check it. Oh, awesome. Now we see 3 topics: ROS-bridge WebSocket, ROS API, ROS API part. Okay, now it's all work, and we can start with our application. For this, we need first one, we should run our ultrasonic distance sensor. But first of all, let me run this. Okay, let me stop our DLC. Oh, it's too close. Let me fix it. Okay. Give me a second. Let me set up my camera. Oh, yes. Sounds good. This is clean. Okay. Okay. First one, Okay, we connected to our Foxglove. Next, run our ultrasonic publisher. For this purpose, we should create several screens, several terminals. One terminal for ultrasonic. Oh, not here. First one, install, setup. Okie dokie, let's add it. Good. Ultrasonic publisher. Now we collect our data from our ultrasonic publisher, ultrasonic sensor. Let's check it. We can check it. For example, we can go to our WebSocket, Foxglove, and first one we can see new topic added, ultrasonic publisher that publish ultrasonic range, and we can add now we remove this panel and change this panel to plot and split it down. Okay, for this plot we add ultrasonic, x-axis, timestamp, y-axis, click to add series, and we add ultrasonic range, and we need publisher, range is yes, and max range. Okay, we set max range, and now we see that blue line appear. It means distance. Now distance is 1 meter, 100 centimeters. For example, if I try to move something in front of my robot, this line will change. Okay. Also, we can add one more measurement, ultrasonic range. Super. And now we see two lines, blue one and orange one. Okay. So now if we move an obstacle in front of our robot, we see that this line change. Okay, and our algorithm, we set that if the distance to the obstacle becomes less than 50 centimeters, we should stop moving our robot and starting to turn right. Okay, let's go back to our presentation. Okay, now we collect data from our real sensor, ultrasonic sensor, and see how it's visualized. Also, we can check it on the terminal. For example, you can call topic echo, and we see that packets goes to this topic. We see timestamp and values. Now distance 16 centimeters. We go away from our sensor. Distance becomes 100. It decreases if we move something before obstacle. So you can visualize it either via Foxglow or via terminal. Next step is to implement run another package called obstacle avoidance. Obstacle avoidance is the exactly algorithm that we discussed. It measures distance and check if it less than 50 centimeters, then it send command to turn your robot right. So we go to the next terminal and run our laser obstacle avoidance. This algorithm publish linear and angular velocity to the motor driver, so we can check this. For this purpose, we go to our Foxglow, our second plot, add series. It's called SimDwell, angular X. Linear X. And now we see it's equal 1. And also we can also add SimDwell smooth, linear X. Okay. So now, for example, if we try to decrease our speed, the forward speed becomes 0. If we try to increase, when it around the 50 centimeters, the forward speed becomes 1. Okay. If we decrease, then we see speed decreases. Okay, go back, and also we need linear speed, and also we need add angular speed, angular z. Good. No. Let's change it. For example, cmd linear and cmd, well, angular z. Okay, now if we change distance, we see the angular z becomes 0.5, and let's add another plot. And change these cmd well smooth, linear x. Super. And this linear well smooth, angular z. Super. Okay, let's check how it changed. Now it becomes above 50. Okay, so we can see that it works. Let me check linear x, angular z, linear x. So we can remove this panel and update this panel, series 3 with smooth, cmd well smooth, linear x. Good. Super. So blue line is the linear x, and we see if distance becomes less than 50 centimeters, it falls to 0, and orange is angular z, becomes from 0 turns to 0.5. If we increase our distance, it becomes more than 50 centimeters. This linear x become 1, and angular z, orange, becomes 0. But it's not too convenient for real robot to start moving rapidly from 1 to 0, from 0 to 1. So we should make it more smoothly. So we add logarithm smoothing to make moving our robot more smoothly, more comfortable. Okay, let's check how it works. We can see this topic not only via Foxglove but also via terminal. So you can go to terminal and see, sorry, not this one, and see what looks the terminal, and we see those packets: linear equal 1, z equals 0, if we decrease our distance, we see linear becomes 0 and angle becomes 0.5. Okay, now it's all working. We should put our robot on the floor and run last one package, last one topic that sends commands from the robot operation system to our obstacle avoidance algorithm to the motor driver. For this purpose, we put our robot on the floor. Put our robot on the floor. Okay. Ta-da! Yes. Let me transform it. Fit to the screen. Now stretch to the screen. Transform. And put it back. Or maybe even not this way. Ah, I got it. My bad. Transform. Fit to the screen. Okay, now you should see our robot. And if we run our application, not this way, but this way. But this way, for example, here we are, and run our robot. We should see how it starts moving. Okay, let me check. Let me check. For example, if we set it in this way, for example, in this way, yeah, it's too small. It's too small. For example, if we try okie dokie, this one, and start again. We'll run it one more time. It start moving. I will make a small barrier. Oh, it's finished. It lost. Give me a second. Not so much. Okay. So we demonstrate here how it works. Now this is stopped. And we can see how it changed. We can also check its telemetry and discuss how it works. Okay, let's back to our presentation. So, as we discussed earlier, obstacle avoidance algorithm is pretty simple, but we decide to add some smooth driving. It means not start moving rapidly and not stopping robot rapidly, but adding some smoothing. For this purpose, we use logarithm function. So when obstacle becomes less than 80 centimeters, we start to decrease our speed slowly until it reach distance to 50 centimeters. This line is represented, so we use logarithm function. Next one is the Kalman filter. Kalman filter help us to reduce noise from the physical sensor. We can check that it represented in our signal. For example, we see blue line is the physical measurement. Let me decrease it. So let me decrease it. We see how it changed during time. Oh, it's beautiful. Yeah, it's beautiful. Let's change y-axis, mean 0, max 100. So we see that is changed. Blue one is the physical measurement and orange one is the measurement updated by Kalman filter. So changes goes more smoothly and it helps our robot to make decision in more correct way. For example, let's analyze this gap. Distance was approximately 18 centimeters. Then it abruptly fall to 9 centimeters, then back to 16. But Kalman filter decide to correct those measurements and make it more smoothly. Kalman filter widely used in sensors. This example represents, for example, green line is the original signal. Blue one is the original signal with that mimics a real signal from the physical device, for example, from the distance sensor. and orange one is the Kalman filter applied to the noise signal, and we see that it makes it more real. It more looks like real signal, but we see the cold start problem because Kalman filters should, to make correct prediction, it should have observations that has been done before, but when it starts it has no observations in the past time, and now because of it makes a wrong prediction. But after a time, for example a couple of seconds, 5 seconds, it collects another measurements and make real predictions, and when it goes along the time it makes more correct and correct. Okay, now let's check our simulator. It could be done via Gazebo-ROS, and we can implement this algorithm even simple with using of Python library GPR EOS0, creating two sensors, distance sensor and robot wheels, and create these two commands, and your robot will avoid your obstacles. If no obstacle, it goes forward. If obstacle detected, it goes backward. Okay, let's compare simulator versus robot. What's the difference? We not always can use real robot, but we can start to learn robotics on the simulator. And main difference between simulator and real robot is inertia. So on simulator your robot can stop immediately, a real robot can't stop immediately. So when you if you create your algorithm and tested it on simulator, when you move your algorithm on real robot, it should be modified to take into account these points, for example inertia. So for example you should increase distance, times, decrease speed, and so on. Low velocity. Sometimes, for example, we can switch to our graphics on Foxglove. We see that blue line becomes 0, but angular speed could be slow too, and in this moment robot can stuck. It neither move forward and neither it turns, so you should handle this situation also. Next one, reflection. Sometimes your robot angle of your sensor on your robot can be low enough, and the signal that's sent by this distance sensor cannot be reflected, and robot think that there are no obstacle before the robot. So you should design your robot and place your sensors in such way to prevent these reflection issues. Okay, this is the end of our presentation. We can answer on your questions if there are any of them, And special thanks for Ross, the Construct AI, the Fox Glow, and Gazebo. Okay, let's try to make some, how it's called, chat notifications. Let's send to the chat. Chat notifications. Chat. If it goes, ta-da! Test message. I don't see here those messages. Leave chat. No messages in leave chat. Looks strange. Another message. Ta-dam. Ah, yeah, I got it. It's not. It's not rendered. So we can stop our presentation. Now we can stop our